stores like product bundles. So this is one package with different decorations. So this is one product bundle. And product bundles are easier to stock onto shelves, to scan, and users don't have to spend a lot of time choosing their decorations. They can just pick one product bundle. Also, if we want to increase our sale, we can pack together less popular shapes and colors with more popular one. But this will create a problem when we want to do production planning. We're usually producing only one color and shape. So we don't want to read data as a bundle. We want to unbundle this data to read only data about this red shape. And for that, we will read a lot of data because we want to analyze our sales. So we will read data for several months or years, and with unbundling of data, that will make our database real slow. Also, because we want to read data of only one shape and color, we don't want then to read data about other shapes and colors. We want to avoid that. Now, let's assume that our transaction is one data bundle. For example, here I have one transaction. We have ID of a product, quantity, and price. So this is one bundle, and we want to be efficient in saving and reading of these data bundles. And for that, we will organize our database into rows. So we can easily read a row or we can easily write a row. So just like putting and taking this bundle on or from shelf, we can also do that with data bundles. But for production planning, we will organize our data differently. We will save our data into columns. So here we have 3 columns: price, product, and quantity. And this is much more convenient for analytics. For example, if we want to answer the question, how much items did we sold that are cheaper than 3 euros, then we just have to scan this first column with prices. We have to find rows where prices are below 3 euros, and then we should find quantities for the same positions but inside of the quantity column. So we will see that we have sold 39 items that are cheaper than 3 euros. In this case, we don't even need to read this product column. We don't need this column. And we can also compress our columns. We can sort them, so that will make our search even faster. When we organize our data into rows, then we have row-oriented databases. And when we organize our data into columns, then we have columnar databases. In companies, we usually save our data into row-oriented databases like Postgres, Oracle, or MySQL. And then after some time, we transfer that data to columnar databases like ClickHouse, DuckDB, or Vertica for the purpose of analysis. Let us now see a difference between row-oriented and columnar databases. When we want to do small writes and reads, then we should use row-oriented databases. So they're perfect if we want to insert one order, to update some user, or to delete some invoice line. Applications are working with objects, and objects are user, an order, or invoice, and this perfectly matches row layout. Rows are great for providing transaction isolation, replication, asset complacency constraints, triggers, and foreign keys. So we're using row-oriented databases when we have a lot of users. They are sending a lot of queries, but those are really simple queries, and users are expecting immediate response. So we are using row-oriented databases for cash registers, for ERP programs, for CRM, for banking systems, and for ticketing. On the other side, we have columnar databases. Then we can read only columns that we really need, and those columns can be compressed, and this will improve our performance. Then modern CPUs, they can process several values at the same time at once, and this is called vectorized executions. So this will improve the speed of our queries. Then we can spread our calculations across several CPU cores or computer nodes much more easily if we are using columnar databases. And columnar databases are used for sales reports, dashboards, for time series and data mining, because in these cases we have less users and they have less queries, but those queries are much heavier. They're using a lot of data, they're having a lot of joins, but the users are okay to wait 3-4 seconds for the result. So we can say that row-oriented databases are better for writing data and providing correctness, consistency, and integrity of the data. But on the other side, columnar databases are better for reading data and analysis of historical data. Let us now see a difference between OLTP and OLAP databases. If we want to prepare a database for everyday operations and transactions, then we will use OLTP database. But if we want to conduct analysis and business intelligence, then we would create OLAP database, and obviously OLTP databases are used with row-oriented data, and OLAP databases are using columnar data. In OLTP databases, we organize our data into a big number of smaller tables, so we will enter each value only once and there will be no duplicates. And because we have a lot of small tables, more complex queries that are using several of these tables will have to join all of them, and then they will be real slow. So in order to avoid that, we do not allow OLTP databases to grow significantly in size. On the other side, we have OLAP databases. In OLAP databases, we merge small tables from OLTP databases into bigger one, and columnar databases are okay with big tables that have a lot of columns and rows. We are trying here to reduce number of joins, so we organize our data into so-called star schema to make our queries more performant. Now, OLTP databases are filled by users and applications in small transactions, and then from time to time we will transfer data from OLTP databases to OLAP databases for the purpose of analytics. So there is a difference in data management. We will fill our OLTP databases continuously, but OLAP databases will receive data periodically and only after data is well reformed. Now, OLTP is acronym for Online Transaction Processing, and OLAP is for Online Analytical Processing. And we saw that they differ because they have different purpose and usage, different database technology, different data organization inside the database, and different data management. Previously, I said that OLAP databases are filled in batches, but that doesn't mean that we cannot do updates or deletes in these databases, and we can apply any of these strategies. The first strategy is to give up on updates and deletes. So we will have immutable data, and this is great because we can pre-sort our data and we can achieve the highest level of compression. And this is used for Power BI. If we are using MonetDB, then we have a database server that is suited for light updates and deletes. In Monet, when we delete some value, that value will just be labeled as deleted. So value will become invisible for queries, and then after some time, our garbage collection will really delete that value. Then we have a strategy where we have our columns divided into small partitions. And then if we want to update a value in some partition, we will actually recreate the whole partition. And this is suitable for companies that have a lot of hardware power. So for example, Google have such ability. So we have a Google Snowflake database server as an example of such database. And at the end, we have the most complex and the most powerful approach. Here we have one database server, but inside of it, we have both OLTP database server and OLAP database server. And when we want to write data, we will write to OLTP database server, but when we want to read data, we will read from both databases. We will, for example, read today's data from OLTP database and historical data from OLAP database. And SAP HANA is an example of such technology. And this approach is called Hybrid Transaction Analytical processing or HTAP. So HTAP means that we have a database that can do fast real-time transactions and also can do fast analytics on the same data at the same time. In the recent years, MonetDB researchers are trying to move MonetDB closer to HTAP category. So they are trying to provide better handling of frequent updates and small transactions, to improve concurrency and snapshot isolation, to make incremental data loads faster, and to optimize for mixed workloads. And today's subject is MonetDB. If you have one server machine, and if you install MonetDB on it, you will be able to run blazingly fast queries, even if you have a lot of data and your queries are complex. MonetDB will do a lot of things for you automatically, so you don't have to worry a lot about indexing, compression, statistic tuning, or partitioning decisions. You will be able to use the full power of SQL, no matter if your tables are carefully modeled or not. You will be able to spend your money on something else because MonetDB is open source database under Mozilla public license. So in one sentence, we can say that MonetDB is fast, complete SQL, easy to maintain, open source analytical database server that can process huge amounts of data on a single server machine. For MonetDB to be fast, we don't need some expensive fancy hardware. For example, MonetDB doesn't have a requirement to keep the whole database in RAM memory. We can only keep in RAM memory data that we are currently working on, and everything else can be on a disk. And thanks to this, MonetDB can handle much more data than the capacity of our working memory. MonetDB will benefit from the fast disk, especially the one that has sustained performance under write load. But we should always make sure to have enough of RAM memory to minimize usage of a disk, because disk is never as fast as RAM memory. MonetDB is specially designed to take the full advantage of the CPU. So when we are running a query or loading a data, MonetDB will spread effort over all of the CPU cores, and it will push usage of the CPU over 90%. If we do not like this, then we can limit the number of cores used by MonetDB, so there is a setting for that. MonetDB will use vectorized query execution. That means that CPU can apply one instruction on a lot of data. And such data has to be of the same data type. This is perfect for columnar databases because instead of one column, all of the values are of the same data type. Then data is processed in small chunks using simple instructions, and this will reduce RAM visits because we can use super fast L1 and L2 memory that is inside of our processor. MonetDB will use late materialization. That means that we will not read not needed data, we will read only data that is crucial for our query. And partial query results will be reused instead of being recomputed. MonetDB is following zero tuning philosophy. That means that many things in Monet are automated. For example, creation of indexes is automatic, compression is automatic, and memory management is automatic. If we are forced to manually create indexes, then we have to know in advance where to create those indexes, and wherever we create them, they will slow down updates and deletes. Because after updates and deletes, we have to recalculate indexes to reflect those changes. And this is especially hurtful for columnar databases because they are not as efficient for updates and deletes as row-oriented databases. And also, if users change their behavior, that can make our indexes ineffective. MonetDB is using a technique called cracking to tune indexes. Cracking means that Monet will group, sort, and index data during select queries. And in all of databases, most of the statements are select queries, and they tend to touch a lot of data, so that is the best time for database optimization. So if we are using cracking, we will best optimize parts of a database that are heavily used, and we will not spend effort on data that no one reads. instead of having one huge indexing job, we will have many tiny incremental reorganizations. And after some time, we will reach a status where all of our data will be optimally sorted and indexed. But if the users change their behavior, then MonetDB will be able to change its strategy and to adapt. And cracking is especially useful for columnar databases like Monet, where each column is stored separately. But cracking is not an ideal solution for every situation. If we have heavy transactional workloads, that will disrupt our cracking method. If we want to achieve distributed processing of data over many computer nodes, that will make cracking hard and complex. And if we have highly unpredictable workloads, for example, if all of the queries are unique, that will limit benefits of cracking. We will now compare MonetDB and Power BI database. Power BI database is in-memory database with columns that are heavily compressed and is optimized for BI models. And thanks to that compression, Power BI database will not have a huge memory footprint, although all of its data must fit into memory. Power BI database can do calculations on compressed data, so it can still be fast while having compressed data, and compressed data will lead to fast I/O. Power BI database likes relationships and measures defined in advance, so it is not good for arbitrary queries, and it is not great for complex joins outside of the model. If we spend some time carefully making our BI model, and if we are ready to wait each time for data to load and to compress, then we will get a database that is best suited for measure evaluation, for filters, and for slice and dice. On the other side, MonetDB is optimized for raw analytical SQL on large tables without modeling overhead. Next, we will talk about some drawbacks of MonetDB. MonetDB is a columnar database, so it is not best suited for OLTP transactions. If we want to run many updates or deletes, then we shouldn't use MonetDB for that job. MonetDB is for analytical queries that would return small aggregated data sets and not for queries that would return huge tables with a lot of rows and a lot of columns. If we have a massive amount of data, then we should use distributed databases. For MonetDB, we should get one powerful computer on which we want to run complex analytical queries. So distributed databases are better in scaling than MonetDB, but because their setup is complex and they must run on a cluster of computers, they tend to have a limited SQL capabilities and other limitations. MonetDB doesn't support replication, but it does support distributed data processing via sharding. Now, sharding will speed up some queries, but not all of them. And if we want to use sharding and partitioning with MonetDB, we must set it up manually and we must be really careful. And because of this, it is much better to use MonetDB on one powerful server machine and to avoid resorting to sharding and expensive network equipment. You should use MonetDB if you want to self-host analytical database on your server, if you want to run complex analytical queries with lot of joins, aggregations, and window functions, if you want to skip creation of BI model and you immediately want a fast SQL, and if you want to avoid vendor locking by using open source software. So MonetDB is best for data engineers, BI developers, researchers, small medium businesses, and Python users. We can use MonetDB with SQL, ODBC, JDBC, and we can send our queries to MonetDB from many programming languages like Python, Java, R, Ruby, PHP. So MonetDB can be easily integrated with your software and your workflow, but the support of third-party clients and libraries for MonetDB is limited. And this is the consequence of the fact that MonetDB is primarily a scientific project. MonetDB was designed and created on CWI Institute in Netherlands, and development was driven by innovation and curiosity and not by commercialization and marketing. And that is why we can say that MonetDB is the fastest database you never heard of. But that development lasted for 30 years, and today MonetDB is complete and powerful database system. In this last section, I have created a list of MonetDB features. But this list is something that is going to change often in the future as MonetDB changes. So I suggest that you go to this blog and to read about MonetDB features there. I also provided links to Word blog posts that are talking about specific features of MonetDB.